Now let's consider the addition of acid to a buffer solution. So say we have a buffer solution consisting of acetic acid and sodium acetate, the salt of the conjugate base. So here we have our equilibrium of the acid with water, and we also have an equilibrium of the conjugate base with water, and we have the autoionization of water We've written all the reactions, the chemical reactions that could easily occur in this buffer solution. Now let's consider the magnitudes of the equilibrium constants for these reactions. So I'll label this reaction 1, reaction 2, and this is reaction 3 for K sub W. So K sub A for reaction 1 is equal to 1.8 times 10 to the minus fifth. Okay, this means that K sub B for reaction 2, as we saw before, is K sub W over K sub A. So that's the equilibrium constant for the conjugate base of the acid, acetic acid. So that will be 10 to the minus 14th over K sub A value, 5.6 times 10 to the minus 10th, and we know K sub W for the third reaction is equal to 10 to the minus 14th. So that just gives us an idea of the relative magnitudes of the equilibrium constants. So we see that K sub A1 is much greater than the other two, so it predominates as far as reactions going to products. So this is the chemistry of what we have going on in a buffer. Now let's add some acid, say hydrochloric acid. So this is strong acid, and so it completely dissociates in water to give H3O plus and Cl minus. The chlorine is a spectator. So this is not an equilibrium, it goes all the way to the right, so I've just written one arrow. Now let's look at what this added acid, which produces H3O plus in solution, can do chemically. And let's look at the magnitudes of the equilibrium constants for the possibilities to find out what basically is happening and what we have to account for in solution. So if we look at this reaction, the reverse of the autoionization of water, this equilibrium constant is equal to 10 to the 14th power. That's huge. So when we add H3O plus to solution, it's going to react with OH minus to produce water. So where can OH minus come from? Well, it can come from reaction 2, or reaction 3. Since there's more OH coming from reaction 2, because the equilibrium constant is greater, then the reaction of H3O plus is going to predominate with the OH coming from reaction 2, and therefore it's going to cause reaction 2 to go farther to the right since H3O plus is consuming OH minus from reaction 2, this causes reaction 2 to proceed to the right to replenish the OH so it can re-achieve equilibrium. And so that means that the concentration of acetate is decreasing because more of it's reacting to try to produce OH that was consumed. And when the concentration of the acetate ion decreases, it's producing OH, but it's also producing acetic acid because it is also a product. So that concentration is increasing. So if we look at the Henderson-Hasselbalch equation, we would have concentration of our conjugate base over the concentration of the acid. And since the concentration of the conjugate base is being reduced by the amount of H3O plus added, and that means that the concentration of the acid increases by the amount of H3O plus added. Therefore, say we start with 0.01 molar acetic acid and 0.01 molar sodium acetate. That's an A there in solution. These were the initial amounts. Then after we add the acid, the constant, need to add, so now we'll add 0.001 molar HCl, which produces 0.001 molar H3O plus. Now the concentration for acetic acid is going to increase by the amount of acid that we add. So we start with 0.01 molar, and it's going to increase 0.001 molar because that's how much acid we added. And the concentration of the acetate ion will decrease from its starting amount by the amount of acid that we added. So we can plug this into our Henderson-Hasselbalch equation, and we'll have 0.01, the starting amount, minus the amount that reacts with the acid, divided by our starting amount of acid plus the amount that's formed from the additional reaction. So that's an easy way for us to find the pH.